Would I encourage young scientists to get into the cold fusion field? Absolutely. It is the future. If you're not prepared for the future, you're going to be left behind. So you absolutely need to get involved. At the moment, that the starting flag was dropped and the race for cold fusion commenced, we were already well down the track. We already understood a lot of the issues that were associated with loading hydrogen and deuterium into palladium.
We started this experiment and being leery because if there was any radiation coming from this could injure us. But anyway, peeking around the corner sort of at the experiment, we could see that the palladium was distorting right after the current was turned on. And having done many electrolysis experiments over a period of 30 years or so, I'd never seen anything like this, so I was intrigued.
I'd been working in the system for 10 years. I understood the deuterium-palladium system. I was in a much better position than anybody else essentially on the planet to know that there was nothing anomalous occurring in the system.
We had evidence of craters on the surface that looked as though there was localized melting followed by an explosion, a miniature explosion.
In any new area of research, particularly one that requires as intense a condition as cold fusion does, there are going to be uncontrolled situations, and there have been half a dozen reports of accidents.
Only half a dozen?
Probably no more than that. There was the original report by Fleischmann and Pons that one of their electrodes melted, in fact melted, broke the cell, melted a hole through the table and was found on the floor underneath the table. Nobody was hurt in that, fortunately, but clearly this is an uncontrolled situation that you would prefer to avoid. Mm-hmm. The most serious accident by far is the one that we had here at SRI. One of my colleagues was killed, in fact.
Was that an explosion?
One of the cells that we were working with, a successful heat-producing cold fusion cell, exploded, but the source of the explosion, the energy which produced the explosion, was conventional chemistry. It was a recombination accident. Now, 99.99% of the time this scheme works very well, but recombiners are dangerous. If they choose to stop for whatever reason, electrolyte splash, some contamination on the surface, or just an aberrant effect, if they choose to stop for a period of time, the pressure of gas will build up in your cell. If the pressure builds up and the recombiner reinitiates, as was the case in the cell that killed Andy, the result of the explosion is, a significant number of grams of TNT or whatever. It's a fairly healthy energy release, or in this case, an unhealthy energy release.
We don't have any material waste.
Right. So it's just these emissions that are...
There is emission, and it's it's a frontier.
The primary product of the cold fusion reaction, helium-4, is not radioactive, it's not hazardous, it's present in the air that we're breathing in this room at 5.24 parts per million. In any reasonable scheme, the increase in helium concentration would be completely insignificant. So the primary product is harmless. We also know that helium-3 is associated as a product with cold fusion reactions, which is also harmless. But we have measured tritium. Tritium is clearly evidenced in a number of experiments, several that have been performed here at SRI. Tritium is a hazard, needs to be managed. There are some neutrons associated with the process, and under some circumstances people have reported various transmutation products, isotope shifts. None of these are very hazardous. Of them, only tritium needs to be handled, and it can be handled reasonably easily. But compared to conventional nuclear power, fission power, the hazards associated with the products are completely negligible, ignorable, and they're far fewer. In fact, the hazards associated with cold fusion nuclear products are far less than the hazards associated with conventional combustion of hydrocarbons.
There's a lot of energy released in this reaction, more than 1,000 times the energy that would be released from a chemical reaction.
Cold fusion is a real effect. We can imagine performing nuclear reactions with about the same facility as we can perform chemical reactions. This is a big change. It used to be that nuclear was the entitlement of the very rich and very powerful in major governmental institutions. Now we've made a nuclear potential for the masses. This has the possibility of commercialization. There was never going to be any possibility of commercializing nuclear technology beyond the way that it had been done in the conventional sense. Conventional fission nuclear power is an extraordinarily crude technology which can never be held in the hands of individuals because it's so highly radioactive and it only operates well on a large scale. So major corporations and governments will wield nuclear power of that sort.
If I wanted to heat my house with cold fusion, so I'd have an apparatus maybe 10 times as large as this, and I'd have a photovoltaic panel on my roof, and with the energy, electrical energy from the photovoltaic, then I could do electrolysis. Okay, and the electrolysis would produce excess heat and hydrogen. Now, hydrogen and oxygen. Now I could use the hydrogen and oxygen in a fuel cell to make electricity directly. So I'd have heat, and I'd be making electricity with the extra hydrogen and oxygen. So that's one possible scenario.
So, and this would be all self-contained in a house? And
Yeah, this would be smallish in size.
Mm-hmm. Right.
A cold fusion cell might be a D cell. It might be like a Coke can.
That small.